It's my pleasure to have with us Luca. I came to know of Luca's work when he was working on embedded systems and low power systems. And in the last couple of years, he has really started exploring the space on trying to create embedded systems for nano satellites and the various technical issues from software to hardware to localization that one would have to address to create wireless solutions for nano satellites. Super exciting work. And it's very rare to have people who actually not just build these embedded systems, but also launch satellites and see that some of these can be operational in the space. So without hogging any more time and space, I wanted to make sure that we welcome Luca. Luca, the floor is yours.
Thank you. So today, I'm really excited to be talking to you about something that I started working on recently. I'm an embedded system person. I've been working on systems ranging from low power, tiny wireless sensors up to quad rotors. And now I'm working on putting things in space in devices that we call nanosatellites. Today's lecture is essentially a very broad and high-level introduction to this area. I'm happy to dig deeper in any of the topics that I'm going to touch upon. You also have my email here. If you want to stay in touch after the talk, I'll be happy to continue the discussion. So before I delve into the details, let me spend a few words about myself. As a matter of fact, right now I have 4 affiliations because I'm an associate professor at Politecnico di Milano, but I have a double affiliation with the RISE Research Institute of Sweden. Then since 2019, I'm on sabbatical at Uppsala University with a part-time job as a senior software engineer at NXP Technologies in the Netherlands. And it's here where this whole thing started for me. So as I was saying before, my work is broadly speaking in the design and implementation of embedded systems that interact with the environment. If you want to know more, you're welcome to check out the website of the lab I'm directing at Politecnico di Milano at noiselab.it. So how did I come to work on nanosatellites? About 10 years ago, I published this paper at IPSN, and I was super happy because it got accepted, because it was the first paper I was writing all along, just right after my graduation. And the topic there was programming what we used to call disconnected operations in sensor networks. Disconnected operations in wireless sensor networks arise in all those scenarios where you cannot continuously rely on a connection with the backend. So your system operates for most of the time in some sort of isolated fashion without the ability to relay the data to the edge or even the cloud. What happened right after that is that technologies like LoRa or Sigfox or all those communication technologies that enable very long communication ranges kind of started to arrive. And the problem I was working on slowly disappeared because it was easier and easier to connect the sensor network to the backend, no matter where it was deployed, because with these long-range communication technologies, you could really reach the sensors almost wherever they were deployed. So the question is, what's left of that work? Well, it turns out that NXP kind of saw this work and thought, look, this guy used to work on stationary sensors on the Earth, but we are right now, 10 years later, facing more or less the same challenges when we put nanosatellites in space, because in that case too, the system works in a disconnected fashion for most of the time, because the opportunities you have to relay the data from the nanosatellite down to the Earth are very rare. They account for, on average, like 2 to 3% of the operational time of the nanosatellite. So they kind of wanted to see if part of that work could be adapted to the specific problems that they were tackling in the design and implementation of software for nanosatellites. So what are these nanosatellites that I'm talking about? What you need to know is that there are two distinct phases in the design of space missions. Until the early 90s, people tried to put a lot of equipment on a few very large satellites. The one you see in the picture on the right is a paradigmatic example of this kind of design approach. The ENVISAT satellite of the European Space Agency managed to accumulate almost 8 tons of equipment. But then people slowly realized that this was not really the way to go, because this kind of design approach caused also lots of problems, because one piece of equipment was generating electromagnetic fields on another piece of equipment on the same satellite. Vibrations of one specific sensing device on one side of the satellite were causing problems on another piece of equipment in another part of this big satellite. Not to mention all the scheduling issues that were emerging, because imagine you have your entire satellite ready to be launched, but there's a little piece that is behind in the schedule, and perhaps the manufacturer hasn't delivered the hardware you needed. So you need to stop the entire mission for a little piece that you're still missing. So the idea of sharing the same platform turned out not to be really a good and wise choice. So people started to think about splitting up the equipment in many smaller satellites. These brought a lot of advantages, because it was easier to isolate the failures. If you have one nanosatellite failing, it's not going to do any harm to the other nanosatellites. It's easier to schedule. It's easier to schedule missions because, as I'm going to describe in a moment, all these nanosatellites are essentially independent of each other. So if you have your nanosatellite ready, okay, you put it on a rocket, you launch it. If it's not ready, you're going to wait for the next opportunity, while other nanosatellites that are ready can be launched anyways. And this kind of approach is also robust to the budget fluctuations. If a group doesn't have the money or runs out of the money, it's not going to block all other nanosatellites that are scheduled to be launched on the same rocket. So there's a lot of advantages in splitting up, dividing up the equipment in the smaller sets. Among the many nanosatellites, there's one thing that emerged as a sort of the de facto standard, and those are called CubeSats. And as the name implies, CubeSats are nanosatellites that are of cubical form. The standard prescribes them to be 10 centimeters high and weighing at most 1.30 kilos. With this specific form factor, you can load a CubeSat in another piece of equipment called the P-pod. The P-pod is basically a carrier of CubeSats. It hosts 6 of them. And the P-pod is designed to be loaded on this nanosatellite launch adapter system that then is put on the rocket that is going to go up in space. When this reaches the target altitude, the adapter system opens up, and the P-pod releases the CubeSats one at a time at the specific point in time that you have planned your CubeSat to be released in that given orbit. The CubeSats started as an educational platform. They started as a means to teach students about all the challenges and trade-offs that appear when designing these kind of devices. But then they proved to be so flexible that several research groups started to explore opportunities to use them as a scientific instrument to do remote sensing from the space to the Earth. This whole thing is viable also because the whole framework and the whole platform is designed in a way to be cheap. If you count all the factors, the cost for building, verifying, and launching a CubeSat may range from 50K to 200K. I'm talking euros, but US dollars will be roughly the same. Keep in mind that, for example, in Sweden, the cost of funding a PhD student is actually higher than that. I'm not saying that I would exchange a PhD student for a CubeSat, but it's essentially to give you a feeling of the cost figures here. This picture gives you an intuitive illustration of the scale of CubeSat systems that will happen to be in space in 5 years from now. This picture accounts for all the planned missions. It assumes that all those planned missions will actually happen. In 5 years' time, we're going to have this density of CubeSats in space, if all those who have planned to launch one do launch one. I was talking to Sean before about the fact that we are, for example, we were scheduled for launch in March, but that got postponed because of COVID. So this is not really meant to happen. And in this picture, even the size of the individual CubeSats is kind of magnified compared to the Earth. But it gives you nonetheless an idea of the scale of the system that will become reality in a few years. So what's cool about that? I find this area fascinating because it really makes everything very challenging. And the reason why is that is the case is because there are so many different dimensions that are strictly intertwined, and you cannot just optimize one without sacrificing another one. For example, let's talk about power. These satellites are powered by solar panels most often. The solar panels are limited in size because you can put them only on the 6 sides of the cube. So you want to manage power very wisely. But then if you have little power and you really need to be careful in managing it, there's not much bandwidth you can rely on because radio communications consume energy. So if you want to have more bandwidth, you need to consume more power, but you don't have much power available. So what do you do? And these kind of trade-offs happen so often in this domain that it becomes very, very challenging and fascinating to be able to work here and come out with simple, I used to say, simple solutions to complex problems, because this is really what we need to do in this domain. So what is exactly on a CubeSat? Let's have a look. There's usually a flight control computer that hosts your computing and communication equipment. Usually, we deploy microcontroller units. If you look at, in the rest of the talk, I'm going to refer mainly, if not always, to missions that happen to be operational at some point in space. There's quite a good fraction of literature that didn't really go the whole 9 yards and managed to launch something in space. So you may actually you may find more information than what I'm going to mention in this talk. But that's mainly because I want to concentrate on things that have managed to work for real in space. Okay, so if you look at the hardware that was actually put in space on a CubeSat, you find MCUs from the little PICs to Cortex-M4. You find memory facilities ranging from a few kilobytes to several gigabytes on SD cards and the like. One thing we need to be careful here is that this is not exactly the same as in Earth. One thing that happens in space is, for example, the fact that when you read and write something from memory, you cannot really take for granted that what you wanted to read or what you wanted to write is actually what happens to be in the memory, because the background radiation in space caused the so-called transient faults in memory, bit flips. So the content of the memory may much more easily than on Earth be corrupted, and therefore you need to put additional effort in making sure that you retain some degree of data consistency. Then you have most often some radio device that happens to be working on the UHF or VHF band, providing bandwidth that, let's say, 80% of the cases that doesn't go above 256 kilobytes per second. So if you take these figures together, you may ask, okay, what is the first bottleneck here? What is the first trade-off we need to deal with? Let's do some back of the envelope calculation. Typically, you put on a CubeSat on a so-called LEO orbit. LEO stands for low Earth orbit, and that is normally considered, a LEO orbit is normally considered between 300 kilometers and 2,000 kilometers altitude. Let's say we are orbiting at 500 kilometers from the Earth. At that altitude, access to the ground stations usually lasts for 5 minutes and for like 10, 12 times per day. With a radio bandwidth of 256 kilobytes, if you do the math, you come to the conclusion that the net amount of data you can transfer across 24 hours is slightly less than 10 megabytes. So it's very little. And where's the bottleneck? Is of course in the radio bandwidth, because for those 5 minutes that while orbiting around the Earth, you have access to the ground station, you can transmit data, you can do it only very slowly. So that's something that we need to take into account. I'm going to talk about this more in the rest of the lecture. What about power? These devices are powered from solar panels that are installed on the 6 sides of the CubeSat. If you consider that for half the time you're not in sight of the sun, and of the 6 sides, not all of them are in plain sight of the sun at all the times. On average, given the efficiency of modern solar panels, you can get at most 1 watt on average. And you may think, okay, but that's a lot of power. What's the problem? Well, the thing is, you need to power, of course, the computing and communication hardware, but also propulsion, attitude and thermal control, sensing. There's a lot of stuff that needs power on a CubeSat, so that 1 watt figure is actually very, very little. And energy is one of the major challenges. Managing energy is one of the major challenges in this domain. People have realized that with these power budget, you cannot use the regular or like mainstream remote sensing technologies, the standard spectrometers, interferometers. They don't work with this amount of power. So there is quite a lot of work in this domain that goes into the design of the actual sensing device in a way that retains accuracy in the sense data, but it consumes a lot less power than what like mainstream technology is used to do. These are some example payloads. Here again, I'm only referring to missions that happen to be operational at some point. Like notable examples are, for example, the SwissCube-1 mission. The CubeSat in that case was carrying an optical telescope. Look at the resolution of the camera. That's the most they could afford given the power budget. But still, with some very clever techniques, they were able to measure the oxygen in the bands within the 100 kilometer range in the upper atmosphere. Another notable example is the Firefly mission. They put photometers on the CubeSat. A photometer is, you know, in a nutshell, a photometer is essentially a kind of a different kind of camera system that they use to do lighting detection. They were able to obtain very fine-grained information on the conditions happening in the atmosphere before and right after a lightning strikes. This was one of the most impactful work in this area. CubeSats move. So we need to be able to control them. And you know what? It's not much different than what happens on the Earth. For any flying device, the control in the 3D occurs by changing the yaw, pitch, and roll by creating moment in these three dimensions. But there's a few things that are not exactly the same on a CubeSat. How do we determine the current attitude of a CubeSat? There are essentially two ways we can do that. We can either use the so-called sun sensors. A sun sensor is basically a device that tells you where is the sun compared to the device where it's mounted on. By knowing where is the sun, you can then compute essentially the orientation of your device. These kind of attitude determination technology is very widespread on CubeSats because it's very low power, even though it's not accurate. 2 degrees of accuracy is actually not a lot. And for example, it wouldn't be enough to do formation flight. I'm gonna get there later. Formation flight on a constellation of CubeSats. So if you want to be more accurate, you need to use the so-called star trackers. The star trackers are, again, sensing devices that allow you to relate your orientation with that of a predetermined set of stars. By looking at those stars compared to where the star tracker is mounted on, you can compute your specific orientation. But these devices are higher power and very expensive. I mean, a star tracker right now may cost up to 30K euros alone. If you think about a CubeSat that altogether costs 50K euros, this is really expensive. Once you've determined your specific orientation, then you need to be able to control it. How do you do that? Well, this is kind of cool. It's one of the most fascinating technology in this area, I feel. Attitude control on a CubeSat is mainly achieved using techniques that are aimed to generate magnetic fields that, by interacting with the magnetic field on the Earth, create a momentum in certain directions. We know from the law of physics that two interacting magnetic fields generate a momentum in a certain direction. So on a CubeSat, we put these kind of devices. They are called magnetorquer. They generate a magnetic field that, by interacting with the magnetic field on the Earth, generate a momentum that we can use to turn the CubeSat the way we want. You may think, I have very little power there. How much torque can I generate with this thing? Is this enough to really to turn it around? Well, there's no drag in space. So even if you can generate a little magnetic field, it's usually enough to make your CubeSat turn the way you want. So these magnetorquer are the most adopted solution because they're small in size. They don't consume power, but because of the way they work, they tend to be inaccurate. If you want to be more accurate, this is kind of a parallel with respect to the discussion we had before about determining your attitude. You can put a so-called reaction wheel on a CubeSat. A reaction wheel is a flywheel that keeps turning at a certain constant angular velocity. While doing that, it doesn't generate any momentum, but at the time you can spin it faster or slower, the non-zero acceleration there generates a momentum that you can use to turn your CubeSat. These reaction wheels are bigger, of course. They're going to consume more space on your CubeSat. They're still low power, but a little more expensive in terms of energy than a magnetorquer, but they're much more accurate. You can really have fine-grained control on the orientation of the CubeSat with a reaction wheel. How do you move it around? The common the imaginary picture that many people have of satellites. I don't know how many of you have watched Apollo 13. I did. You know, you imagine satellites with like pretty powerful propulsion systems that are controlled by the pilots on the satellite to move in space. Well, on something that is 10 centimeter size, it's not really possible. Most CubeSats do not have any propulsion system. They are put in orbit by the mother rocket when the P-pod opens. And because of the interaction with the gravitational field on the Earth, they'll keep orbiting around the Earth until either the control center decides that it's time to kill it, and then it will be destroyed on the way to the Earth as soon as it enters the upper atmosphere, or it will just keep orbiting on the initial orbit. There's a few examples, though, of propulsion systems that were deployed on CubeSats, and the most notable example is this device that's called NanoPS. It's a miniaturized gas thruster that uses a very specific mixture of gases. And with this device, the people who put it in space managed to have some little control on the general mobility of the CubeSat, but it was full of problems because, you know, this thing tends to be bulky. This thing is actually 10 centimeter in size per se, and 5 centimeters deep. So it's half the size of a CubeSat that you invest only in the propulsion system. And there's a lot of other problems. For example, the performance, the amount of torque that you get actually varies with the amount of gas in the tank. So it's really difficult to really understand how much torque you're getting at a certain point in time. And in any case, these kind of devices are sufficient for formation flight. They're sufficient if you want to perform small corrections on the orbit. They're not sufficient for general operation. You cannot just toss the CubeSat around the way you want with this thing. It's not just powerful enough. How do you determine your position in space? Well, here again, there's a bunch of problems that we need to face. And this is the area where my group has specifically worked. Let me start off with a few numbers. So a CubeSat on a LEO orbit travels at speeds ranging from 7 to 15 kilometers per second. That is faster than a bullet. The GPS satellites travel at roughly 3.8 kilometers per second. They orbit at higher altitudes, but still they're kind of fast when compared to the relative movement of the CubeSat. I'm not sure how familiar you are with the functioning of the GPS system, but whenever your GPS receiver needs to compute the position, the first thing it needs to do is to find the satellites to lock on. And that happens by identifying what's the Doppler search range. But with these two things traveling so fast with respect to each other, the search range that is normally 10 kilohertz on the Earth increases to up to 8 kilohertz in space for a CubeSat. So there's a huge range of different frequencies that, because of this Doppler effect that happens in space, you need to search through to find the GPS satellites to lock on that would be useful to compute your position. But that's not enough. To make things work, to make things worse, actually, if you don't have any way to control your attitude, or your attitude control is imprecise, a magnetorquer gives you 5-degree accuracy, so it's not precise. If you cannot precisely control your attitude, then your CubeSat is very easily bound to be tumbling around. That means that the orientation of the GPS antenna compared to the GPS satellites is going to change over time, continuously. And because of that, the visibility on the GPS satellites will change as the CubeSat tumbles around while orbiting around the Earth. And finally, the GPS takes energy. On a normal satellite, on a bigger satellite, you would duty cycle the GPS receiver anyways because it's really energy hungry. If you do it here with all these problems, you end up with a situation where the so-called time to the first fix, the time it takes for the first position information you are able to compute, becomes much longer. And because of that, you need to keep your GPS receiver on for a much longer time, and therefore you're going to kill the battery. So we tried to make this whole thing more efficient. We built an actual custom GPS receiver that we call Hummingbird that we expressly conceived for operation on a CubeSat or a nanosatellite, generally speaking. This is the prototype hardware that we developed. We used a Star Trek Venus GPS receiver coupled with a Cortex-M4 core. And we were able to output navigation data plus the raw GPS signatures onto the control systems at 1 hertz, once per second. That's usually enough for general operation of a CubeSat. The most difficult thing we had to do in terms of hardware design was to make it small and lightweight. Here you see Hummingbird mounted on the side of the CubeSat that we used for experimentation. With a big leap of fantasy, this CubeSat is called NanoSat. We had to stay, so the people who built the rest of the device had given us a power budget of 150 milliwatts. They stayed there by a small margin. And the whole thing was actually cheap, 200 euros. You can build it. But the intelligence here, the really novel part of the system is, I believe, in the way we handle the data. So what we do to make this whole thing efficient and reduce the time to the first fix is based on the idea that, at least to some extent, you can, in a way, emulate the orbital behavior of a CubeSat without actually continuously checking the GPS data, but pretending that you know the GPS data and you propagate the movement of the CubeSat in a simulated environment that helps you getting GPS data more efficiently when it's time to do so. What we do concretely is that before the launch, we load the Hummingbird device with TLE information. TLE stands for two-line element. A two-line element is a 138-byte data structure that describes the orbit of the CubeSat. The TLE intuitively tells you the trajectory of the CubeSat as it travels in space. Plus, we load the almanac of the GPS data. The almanac is a representation of where the GPS satellites are supposed to be at a coarse grain level. These two information are used together the first time we turn on the GPS to find the best visible satellites, or those satellites that we think are going to be visible when we turn on the GPS. By doing that, we essentially restrict the search space in the Doppler search range. Instead of searching throughout the whole 80 kilohertz, we are able to identify 4 or 5 GPS satellites that we think are going to be visible when we turn on the GPS. Because we bet that those GPS satellites will be visible, we immediately try to lock onto them. And that actually works out most of the time. By locking on to those GPS satellites that we think will be visible, we can much more rapidly acquire the rest of the data that is necessary to compute the GPS position. The rest of the data is the ephemeris information. The ephemeris information is the data that describes the GPS satellite position at a very fine grain. And all those information required to time synchronize with the other GPS satellites and finally compute the position of the CubeSat. Once we have done that, we turn off the GPS, because at that point we have the position, we have computed it, and we propagate the state vectors, meaning we continue the simulation of what we think is going to be the orbital behavior of the CubeSat. Next time we turn on the GPS, this state vector propagation will allow us to say, okay, at this point, we bet that those other GPS satellites are visible, and we try and lock onto them directly without searching through the whole Doppler search range. It turns out that the TLE information, the information that describes the orbital behavior of the CubeSat, needs to be updated every once in a while because the orbital behavior is not perfect. It doesn't follow precisely the state vector propagation. So every once in a while we need to do that. But altogether, this allows us to get position information much more efficiently from an energy perspective, because we reduce the time we need to keep the GPS receiver on to get the first fix. What's the impact of this? In this plot, you see data we got from the actual operation of the satellite. On the y-axis, there's energy consumption across 5 hours of operation. The leftmost column is the energy you would consume if you would keep the GPS receiver always on. That is a sort of a baseline for us. If you have no duty cycling in place and no smart technique to save energy, that's the amount of energy you would consume from the GPS receiver alone. If we duty cycle GPS receiver every 50 minutes, but without using Hummingbird, we just switch it on and off, this is the amount of energy you would consume. If we use Hummingbird, and especially this vector state propagation, this is the energy you would rather consume, which is like a manifold improvement compared to both the baseline and the naive duty cycling approach. Let me then, in the interest of time, I'm gonna briefly mention communication issues here, but there are plenty actually. There are different ways that CubeSats need communication. You may need communication to the customer premises because you want to relay the sense data down to the Earth. You may need communication across CubeSats if your application logic is spread across multiple CubeSats. You may need communication to some other station on the ground for different kinds of sensing functionality. These different flavors of communication have different requirements and were fulfilled with many different technologies that are reported in the literature. So as a matter of fact, when you talk about communication in CubeSats, there's a huge melting pot. Despite the best efforts of the CCSDS, that stands for the Consultative Committee on Space Data Systems, those poor people are trying to standardize the way CubeSats talk to each other, but it's so difficult that we'll have to see if they succeed. So, for example, in terms of antennas, you find anything from microstrip antennas to beam steering antennas. Most CubeSats use RF, but there are prototypes and even operational systems that use lasers and visible light, especially for CubeSat to CubeSat communication. Pros and cons are intuitive here. For example, I mean, in RF, you don't really need fine-grained orientation of the antenna. With lasers, you do, and with visible light as well. The range of frequencies people use, I mean, the range from VHF to millimeter wave. And even though with RF you tend to obtain kilobits per second bandwidth, with lasers across CubeSats, people have demonstrated even gigabytes per second. And modulation schemes vary from like simple CDMA to very sophisticated TMA schemes across the whole constellation of CubeSats. These are some examples of the trade-offs between RF and lasers. These are, in a way, these are arguably the two extremes when it comes to communication on CubeSats. And something worth mentioning is that these technologies are often combined together on the same CubeSat. There's many CubeSats that have, for example, an RF communication system for relaying data down to the Earth, and a laser to talk to other CubeSats. So these things tend to be combined. And finally, I want to mention the fact that everything I talked about so far was mainly related on a single CubeSat, but there's a lot of potential when you put many of them together, achieving configurations that are called constellations of CubeSats. And here, one of the main challenges is how do you coordinate them in space? There are many different ways you can plan their trajectory to achieve a certain degree of coverage of the phenomena on the Earth you want to monitor. So the simplest is the so-called Walker constellation. A Walker constellation is intuitively represented in the picture here. They are all uniform orbital trajectories. They're the same for all the CubeSats. Because they're so simple, they're ellipses essentially, they're easy to implement. You don't need much attitude control or very fine-grained attitude determination to be able to coordinate a constellation that way. But it can be mathematically proven that if you want to achieve global coverage of the Earth, that is the configuration that is going to require the highest number of CubeSats. A different approach is the so-called street of coverage constellation. These are parallel orbital trajectories. These are easy to implement too. They require fewer CubeSats normally, but they do not give you uniform coverage because the coverage will be higher at the polar location, and at the equator, coverage will be poor. So if you want to have global coverage with the least number of CubeSats, you need to implement the so-called flower constellations. The flower constellations are these kind of trajectories that look like flowers indeed. They allow you to have global complete coverage of the Earth, but the shape of the trajectory is actually quite complex, and it's difficult to implement because you need to have very accurate attitude determination and control. And depending on the number of CubeSats you put there, you may need also propulsion to be able to kind of shape those trajectories in the right way. This area is fascinating. Besides the missions and the operations that have happened in space up to now, there's a lot you can dream about, and people have been dreaming about the so-called Internet of Space things and those kind of things, where the idea is that as we put more and more of these devices up in space, we'll be able to extend the internet we have on the Earth up to space. And it's not because I saw the question on the chat before, but one mission, for example, that is foreseen by, that is planned by NASA, is to put a constellation of CubeSats there to act as intermediate gateways towards the bigger satellites that are planned to reach Mars in the near future. So extending our internet up to Mars in a way. And in building these kind of systems, people are envisioning even like adapted or new protocols to run these kind of networks. There's people who try, for example, to use MQTT between the Earth and a constellation of CubeSats. There's people who try to put co-op servers on CubeSats to have a like more expressive interface to control the device. There's a lot you can imagine here. So I want to conclude here by giving you direction. If you want to learn more about this technology, you don't need to put a CubeSat in space. There's a few very nice initiatives that give you kind of tools to learn more about this technology. And one that I want to mention is this initiative called the AMSAT CubeSat Sim project. Even though it's called CubeSat Sim, it's not a simulator. It's not a software simulator. This project is providing, as in a completely open way, everything you need for building your own small CubeSat that simulates a certain predefined application and transmits data on the VHF band. There's everything there. There's like the schematics for printing the CubeSat with a 3D printer. There's the bill of materials for building the boards. There are instructions to put all these things together. It's a very nice learning experience that I would encourage you to undertake if you're interested. You're going to learn a lot in the process. So this concludes the lecture, and be happy to answer any question. I've seen some in the chat.
Thank you so much, Luca. This is extremely, it's great that you basically put in a way in which you could educate all of us. I learned a lot about this space from your talk, so this is great. Before I go on to the questions from the chat, and as they're coming in more and more, I would like to start with my own questions. I know that you guys have already deployed a couple of satellites into space. So can you speak a little bit about your experience there? What is the process which goes into like doing that? If a student, a grad student, or a faculty who hasn't worked in the space in this area wants to do it, what are the pitfalls? What is the timeline? All that good stuff.
So I don't want to downplay what we did, but as a matter of fact, we put one in space up to now. But okay, keep in mind there's no standardized procedure or schedule or anything. Everything starts from getting in touch with your own national space agency. In our case, part of my team is from India. They had previous connections to the Indian Space Agency, so we went through that channel. I mentioned before we're trying to get in touch with the European Space Agency too. But you get in touch with them and ask if there is a planned launch of CubeSat equipment. At that point, they'll tell you, yes, we have a rocket that is planned for that specific date. It has, I don't know, X available slots. Do you want to take one? Do you want to reserve one? Then you say yes, and then the whole thing actually starts. Because at the time you say yes, you're supposed to sign an agreement with the space agency where you commit to provide certain parts of the CubeSats at certain specific points in time. For example, the first thing you're supposed to provide is the specification of the CubeSat that you want to put on the rocket. That's a document that basically says how much it's going to weigh, or what kind of equipment you plan to put there, what kind of RF or generally speaking electromagnetic interference it may possibly generate, everything that they need to know of your CubeSat to plan the launch. Of course, there is not carved in stone. You can revise the document. There are specific points in time from the point you submit the first version of the document up to the date of the launch, where you have the opportunity to revise that specification, but it's important that you get it right as soon as possible. Then they will tell you that, for example, they want to have all the computing and communication equipment without the actual satellite, but they want to have it by a certain date, and they want you to go there and spend a couple of days with them, showing them what it's going to do, how it's going to communicate, so they can measure what happens, mainly in terms of RF RF interference. And there's a number of steps like that until you get to a point, usually 4 months before the actual launch date, where you're supposed to go there with your CubeSat all together, with everything basically ready to be left there, and then it's in their hands. They're going to put it on the P-pod, and the P-pod will be loaded on the rocket. And as soon as the CubeSat is released and it turns on, you will get a notification from them. And believe it or not, most of this works by email. It doesn't feel much modern, but very modern, but it does. It does work like that. You get an automatic email from their system saying your CubeSat was released at this point in time, UTC, blah, blah, blah. And at that, for example, with the Indian Space Agency, they have a network of ground stations that push the data on an Amazon Cloud instance, and you can find your data there in byte form. This way of working is the one when the satellite doesn't require any active control. So once it's released, you're only going to get data. If you want to send data, I cannot speak from direct experience because we haven't done that. But if you want to send data up there, there's an additional procedure you need to go through, and they will give you access basically to an API, again in some cloud infrastructure, that then they take care of connecting to the CubeSat through their network of ground stations. Everything is very much, it's very not direct at all. It's you need to trust that their system work the way they're supposed to. You need to trust them that they will do what they stated. I was used to have like direct access to the device. That's not really the case here.
We have a question from Suvesha. Suvesha, do you want to ask the question?
Yeah, sure. So I had two questions. One was about the solar panels. So there was work from NASA about using the Moira origami techniques to kind of build huge solar panels that could open up, can be deployed passively on the space, and they don't really weigh a lot. Have you explored those methods to increase power consumption, or is it feasible on the CubeSat or nanosatellite range?
There's a CubeSat from the Canadian Space Agency that was launched a couple of years ago with that specific equipment. If you read their paper, the feeling you get is that they probably don't think it's worth it, because it's true you get more power, but the additional power you get, you're going to invest into attitude control, because the wings makes the CubeSat more difficult to keep in orbit. Okay. So it's feasible. They have demonstrated it, but it's unclear if it's worth it.
Okay. And the second question I had was about passive propulsion. If I understand correctly, a lot of CubeSats use passive propulsion techniques because they're so small in size. Have you considered electrolysis propulsion for CubeSats? That was a work done previously by a CubeSat from Cornell a couple of years back. So is that feasible at that range, or is it just a proof of concept at this stage?
I think there's one group from Israel, I think, who put that in space and demonstrated it works. Okay. Keep in mind that the design of a CubeSat is rarely the effort of just one research group. In our case, for example, Nanosat was the result of the work of 4 research groups. We were in charge of positioning and then GPS. Other people were in charge of other parts of the CubeSat. I would like to explore that. I just didn't, that kind of things. I just didn't have the opportunity, and in full honesty, I would need an aerospace engineer or mechanical engineer to help me out, because I'm a computer scientist by training, and I'm not sure I know enough of those things.
Yeah, sure. Thank you.
So we have a question from Alex from the chat, which is, you mentioned how radiation in space can cause issues with memory corruption. Could you talk a little bit more about how people mitigate these issues? For example, do you use radiation-hardened computing hardware, or do you adapt consumer-based hardware by running different algorithms or error correcting codes?
So the short answer is lots of CRC. Radiation-hardened equipment is usually too expensive for the budget of the people who do this kind of things. CRCs are efficient to compute on embedded hardware, and have been demonstrated to be reasonably efficient at catching these kind of errors. It's one thing that I thought was nice in this area is that there is a whole literature in dependability and dependable systems that was kind of was going to be forgotten in a way, because the dependability we have on mainstream hardware on the earth is so high that most of those things are kind of unnecessary. But now we have a new place where those things are useful again, and all those kind of error correction codes, all those kind of things, typically in software, are the way people tend to tackle those issues.
I see, and that's kind of cool. One other follow-up from Ton is, did you consider using hardware for optimizing the performance of the CRCs, or is that not really an issue in terms of power consumption for doing lots of CRCs?
The thing is, CRCs are already very efficient on common embedded hardware. On a Cortex-M core, CRCs are really efficient already. On MSP430 MCUs, they're efficient already, and that's basically the cheapest way you have, and reasonably efficient to tackle those things, those issues.
So there's another question, which I think is actually for me, which is, you talked about nano satellites, which seem to be a few centimeters, a little more than a few centimeters. Are there any efforts to go even smaller, or is there a need for going any smaller?
So there's a whole range. And the smallest that is space proven is so-called the femto satellite. A femto satellite is supposed to be 2.2 centimeter size, if I'm not wrong. So it's tiny. It's a dice, basically. The question is always, what can you do in that size? In terms of remote sensing, there's not really a lot you can put there, because most of the remote sensing technology we have is much larger than that. I would argue that it's interesting for now to see how much you can push the envelope there. How much they are practically useful for real applications is something that we'll need to see.
Yeah. Another question which Amy had is, how long can you talk a little bit about how long these satellites usually stay up in the space? And if you have to recover them or repair them, is it just you just discard them, or do you actually try to fix them somehow? Are they programmable? Like, can you actually try to program them all the time? Yeah, all that stuff.
Programmability is out of the question, because to be able to program them, you would need to kind of have the ability to interact with them sort of in real time, and you can just forget about that. Even the control that I mentioned before happens on a minute scale. So you send a command there, you wait 2 or 3 minutes, you get the answer back. That's the kind of time scale we're talking about. So it's a good question. How long do they stay up there? If I'm not wrong, in the longest running CubeSat up to now is one from ESA, European Space Agency. It used to be operational for 9 months. After that, what happens usually, in most of the cases, is that something goes wrong there, up there. You lose control of it. It stops communicating. And what's going to happen in that case? It will at some point change the orbit and be attracted to the Earth, and it will disintegrate as soon as it enters the upper atmosphere. As far as I know, there are no efforts at retrieving them back. It wouldn't even be worth it. There is an issue, though, that is called the space debris, because there's a lot of stuff up there that is basically dead and hasn't fallen back yet. It keeps orbiting, and it's so much becoming a problem that people have started to talk about collision avoidance in space, because you need to make sure you're not bumping into any of these things.
That's actually kind of the questions a couple of others had as well, which is once you start putting all these reflective material up in the space, does it actually affect astronomy, which you're doing from the ground up? Does it? It's not.
That's actually something that people are debating quite a lot. I mean, if you remember the picture I showed at the beginning of the lecture, the more stuff we put up there, the more we are going to pollute the space. Yeah, sorry.
And like, are there other legal challenges? Like, is there any? I mean, what would prevent from, in terms of radio signals, in terms of sensing? Is there a specific power which the world organizations have agreed that you can't transmit more than a higher power to prevent interference, similar to what Wi-Fi does? Do you have similar things for sensing, that to prevent privacy issues and so on? Are there any such regulations?
The CCSDS is trying to standardize is trying to promote a set of regulations where they say that at least for RF, you should not use more than 1 watt of power for transmission. But again, it's sort of Wild West there. Even if they standardize this, nothing says that people will stick to it. In terms of privacy, I'm not aware of, investigations in the implications on privacy of, having so many things up there that keep an eye on you. But it's definitely a potential problem, something we'll have to deal with at some point for sure. In many ways, the situation here reminds me of the kind of early days of programming big mainframes. There's really no specific rules or so many problems that people are kind of underestimating. That, I mean, there's a lot probably that we're going to see in the next few years happening in this area, because we are slowly discovering things and then working on new problems or old problems in a new context.
So the other thing which really fascinated me in your talk was about the whole networking. You talked about this architecture where you can talk between these CubeSats and also to the Earth. And you mentioned like people can explore things like RF, millimeter wave, lasers, and so on. And they have issues with alignment if you're using lasers, but RF probably has range issues. But I think it's also probably easier to do radio signals in the space because there's no multipath, I'm assuming. So it's probably a little bit, you wouldn't have, in terms of localization and so on, using radio signals, you can probably just use things like distance, signal strength to get the actual location between CubeSats. So people started working on those kind of spaces. Let's say I'm actually going to deploy multiple CubeSats. Can I localize what the positions are with respect to each other? And what kind of applications could you think of in terms of distributed computing across all these CubeSats, for example? What are your thoughts on what are the application people are considering and so on?
So there are efforts at localizing CubeSats with respect to each other, so that you have a GPS information on only one of them, and then you localize the other relative to the one with the GPS receiver. Mm-hmm. In a nutshell, the fact is, it's true there's no multipath, but the regular free space propagation model do not work in space, because you get the effect of the different layers of the atmosphere up to the point where your CubeSat is orbiting in terms of background noise and interference. There's a whole literature on RF propagation models for space. Those are the models that are used in those kind of works where they do kind of two-way ranging between CubeSats to find their relative positions and those sort of things. The distributed coordination that you want to achieve in those cases is mainly because, I mean, the final goal is most often having global coverage of the Earth with the fewest number of CubeSats. That is not for granted, because these things drift while orbiting, they slow down, they go a little faster, depending on how precise is their orbital plane. And the LEO orbit makes this more complicated, because the farther you are from Earth, the less you are subject to this kind of phenomena. But the CubeSats would not survive so far from the Earth. They would not really be able to talk down to the Earth, because the distance will be too large. So the 5 kilometer range from the ground is where most CubeSats are currently deployed, and it's a trade-off between the ability to talk to the ground and not being too subject to all this kind of nasty phenomena due to this peculiar environment where you're operating.
I see. Sisto had a question on, can you just reuse some of the 5G hardware people are trying to design for communication, or do you have to design custom hardware? And he's also talking about potentially combining it with quantum communication on CubeSat. I think China is trying to do some of these things where the Chinese researchers are trying to do quantum communication of secret bit exchange from the space. So if you had some thoughts on that as well.
So I'm not an expert in quantum communication, so I'm not really sure I can say a lot about that. What you should consider is that the regular communication systems, the cellular systems, they're designed for quite different requirements. For example, in 5G, the design seeks to increase bandwidth, minimize latency in a scenario with a lot of terminals. Here's on a CubeSat, that's not the case. There's really a few of them. Yes, it would be nice to have a lot of bandwidth, but that's not really the major goal. The major goal here is really to do things with the least energy cost. And you're not going to have constant connection to the ground anyways. On a cellular network, there's always one base station you're connected, at least one base station you're connected to. In space, you're going to spend most time not being connected to anything. And then doing your own thing without being able to talk to anyone else. So the cellular requirements is sharply different, and that's the reason why, for example, cellular technology, as far as I know, is not really widespread in space.
One final question before we let you go is from Ian, which is, what are your thoughts on the Starlink program, specifically in terms of their implementation or on the concept of using small satellites for global internet access?
I think we should separate out the hype from the actual technology progress. Based on what I read about the project, it's the kind of technology they want to use is something that was already space proven in previous missions. It is true that they're putting together a very nice system, and if they achieve to do that, it will be nice, because they're going to provide access to places where it's difficult or even impossible to connect to the internet. In terms of scientific progress, there's honestly not much there. I'm not lowering my volume because someone is listening, but I think it's probably one good example where we see the products of research being packaged together in something that can be delivered to the final user and provide a benefit, a real benefit there.
Thanks a lot, Luca. This is extremely helpful, and thanks
You're
a lot
welcome.
for taking the time to talk to us, and hopefully you can get a good night's sleep now.